Imagine your Python code running like a smart home. Lights, doors, sensors, all working together. That's object-oriented programming. In this session, we will explore object-oriented programming in Python using a smart home analogy. We are going to master the 4 pillars of object-oriented programming and break it down using one delicious idea. Object-oriented programming is a PI: abstraction, polymorphism, inheritance, and encapsulation. I have posted the code in the description, so for now, just focus on the logic instead of coding along. I'm going to show you the rough draft process that you usually don't see in the final version. I'll be using a Jupyter Notebook for quick testing and regular Python file for the final build. If you want to learn how to install Anaconda or create a customized A.P.I.E kernel for Jupyter, you can follow the other videos I have linked in the description. But for now, you don't need to worry about anything. Jupyter comes as a built-in option with PyCharm. Open PyCharm, create a Python file called Smart Home. You can also create a Jupyter Notebook called Experiment. Split the screen to the right and put the Jupyter Notebook there. Now think of your smart home. Every device has a blueprint, actions it can perform, and rules it follows. Now look at this kitchen light. Consider it also has a blueprint, and we can think about a class that is called simple device. We start with the keyword class. This creates our blueprint. Inside, we define a special function called init, a special initializer method. This is the constructor. It runs automatically when you create a new device. We set self.isOn equal false. This word self is crucial. It ensures we are talking about the specific device's data, not all devices. Next, we add a behavior, that is a method, and we call it flip switch. It simply reverses the state. Now we can use this blueprint to create a real world object. For example, kitchen light equal simple device. That's how we create the object in Python. Now every time we call this flip switch method, it changes the light on or off. Now that you understand how classes and objects work, let's scale up. Instead of one simple device, we want a whole smart home system. Light, speaker, thermostat, all working together. Before writing code, professional developer creates a plan, and that plan is usually a UML class diagram. You don't need to learn UML in this session, just understand the idea. Look at the box at the top. That is our parent class, smart device. And the boxes at the bottom are the children, smart light, smart speaker, and smart thermostat. This diagram tells us exactly what code to write. Let's slice the pie. A is for abstraction. Abstraction is about hiding complex details and showing only the necessary features. When you use a smart plug, you don't need to know the voltage or Wi-Fi protocol. You just press a button or use voice command. In Python, we use an abstract base class to enforce this. Look at this diagram again. Smart device. This is the parent class and this is our abstract class. That's why you see this A letter before the class name in the UML. Let's import ABC and abstract method from the ABC module. In modern Python development, ABC, which means abstract base classes, is used to create a formal contract between a base class and its subclasses. While you may not have needed it for smaller script, it becomes essential as project scale. Create the class smart device. Notice we put ABC inside the parenthesis. As we mentioned, this stands for abstract base class. We are telling a smart device to inherit all the features from ABC. We are effectively signing a contract with Python that says, this class is just a blueprint. Do not let anyone build a smart device directly from this file. Inside the class, we add init constructor. And this time we are also adding a name parameter. So this will enforce like giving every device a unique identity. For example, if you create a light, you need to mention it as a light, thermostat, and now we need to save it. So we use self.name so that we can save the device name. And we also add two more variables here to set the status of the device. Now let's create a method called connect to Wi-Fi. If you want, you can add disconnect from Wi-Fi also, but for simplicity, I'm just adding the connection function here. Next, we define turn on. For now, I'm just writing pass. And we also add another function called turn off. Right now, turn on is optional. A child class could ignore it if it wanted to. But remember, we also imported abstract method here. So let's put the decorator add abstract method just over the turn on function. This enforces abstraction and it tells us the parent doesn't know how to turn on, but every child must figure it out. Due to ABC being inside the parenthesis of the smart device class, it becomes a blueprint. We told Python, don't let anyone build a smart device directly. Let's see what happens if we try to do that. Let's create an object called light equal smart device light. Remember this name argument inside the initial constructor function? Yes. Due to that, we need to provide a name when we create an object. Run it, and we get a type error saying can't instantiate abstract class smart device without an implementation of abstract method turn on. That's how ABC and abstract method stick to the contract and prevent us from creating an object from the abstract class. How about we create a child class then? We define another class smart light and in the parentheses we put smart devices. For now, write nothing else for this class, just pass. Create the light object. This time instead of smart device class, we will use the smart light class. Run it. We get the type error again because this smart light didn't create the turn on function. This actually was enforced by the decorator abstract method. Let's add the turn on function for a smart light. Run it again and this time we don't get any error. Call the turn on function. Run it. Oh, it's working. Check the turn off function. Both are working fine. This is the abstraction of object-oriented programming. How about another pillar of object-oriented programming? I for inheritance. Look at this SmartLight class again. Did we write any code for turn off or connect to Wi-Fi inside the SmartLight? Or how about the name? We put light inside the SmartLight when we created the object, but there is no name variable inside the SmartLight class. So all the variables come from the abstract class, smart device. We can say these variables are shared attribute. These methods are also related to inheritance. So let's put a comment inheritance here in the SmartLight class. In the UML, smart device is our abstract class. And for the subclass, we created SmartLight. In the base class, we didn't create a fully operational turn on method. So we created that in the child class. Let's see the demo. Call the connect to Wi-Fi function and put the argument my home 5G inside the function. Run it and we see that it is connected to the Wi-Fi. Now imagine if you had to write the code connected to Wi-Fi from scratch for every single new gadget you bought. This is a waste of time and violation of the DRY principle. That means don't repeat yourself. In our smart device base class, we write the connect to Wi-Fi logic once. Later, when we create a smart light, it inherits the ability automatically. It gets the Wi-Fi code for free without us typing it again. So if you look closely at the sidebar in PyCharm, you will see this little icon next to our class. That tells us smart light is a child of smart device. We didn't write the Wi-Fi code here, but PyCharm knows it's there because of inheritance. Create the smart speaker in a similar way. Create the object from it, connect it to the same Wi-Fi, run it. So both the light and speaker devices are created and connected to the Wi-Fi. As we have discussed inheritance, that leads us to P for polymorphism. Poly means many, morph means forms. So look at our turn on method. For a light, turning on means glowing. For a speaker, turning on means playing music. Polymorphism allows our main system to treat all the devices exactly the same. How? Let's put the light and the speaker inside a list called devices. Loop through the list and call the same method turn on. They each know exactly what to do. And now look at the output. The light is glowing and the speaker is playing your favorite playlist. So far, we have discussed about abstraction, inheritance, and polymorphism. Finally, let's focus on E for encapsulation. This is about protection. You don't want a guest in your house accidentally resetting your device's firmware or changing the voltage to unsafe level. So let's create a smart thermostat. Here, inside the init method, we at first call this super init method to make sure the parent setup runs. Then we define extra variable that is self dot double underscore temperature. Notice these two underscores? Yes, in Python we encapsulate data by making it private, and usually by adding two underscores before the variable name. So this restricts direct access. You cannot access it directly from outside the class. So we use getters and setters to control how that data is changed. To allow the safe change, we write a setter method called setTemperature. Here we add logic. If new temperature is greater than 60 or less than 80, that times we allow to change the temperature. So this ensures new temperature can only change the setting if it respects the logic here. The getter method is simple. We are just returning the private variables temperature. Look at the UML one more time. Look at the thermostat. Do you see this minus sign here next to the temperature? In UML, a minus sign means private. And with that, we have finished this whole diagram. Let's test this thermostat also. Create it, connect it to Wi-Fi, and add it to the devices list. Run it. Perfect. Now let's test the encapsulation. We will have three types of test here: safe change, unsafe change, direct access attempt. For the safe change, we tried a new temperature of 75 degree, which is in the range of 60 to 80. So it allows us to change the temperature. But for the unsafe change, when we tried 500 degree in the main block, the logic rejected it. So we are protecting the data from bad input. For direct access, let's use a try and accept block for the test. So when we try to print the private variable directly, it throws an attribute error. As we have checked all of this, let's put this whole block of code inside the if name equal main block so that we can import this smart home script as a module in other programs. You have just finished your whole smart home project and learned object-oriented programming in Python. So next time when you are coding, remember A.P.I.E. Abstraction hides the mess, polymorphism lets different objects respond to the same command, inheritance prevents you from repeating code, and encapsulation protects your data. I have put the full smart home source code in the description below so that you can copy paste it and try it yourself. Thank you. Happy coding.